All right, let's get started. Hi, everybody. My name is Jennifer Cunningham. I'm the AVP of Alumni Relations here at Lehigh. Thank you all for joining us for this, what will be a fascinating half an hour. Our guest today is Professor Javier Buceta. He has been at Lehigh for about 4 years, came to us from Madrid, Spain, and has also been at USC San Diego and at Barcelona and the Salk Institute. He is the Associate Professor of Bioengineering and Chemical and Biomolecular Engineering here. And you have probably read in the news or seen on Stephen Colbert or in the New Yorker. He's been all over the place talking about this amazing discovery that he made in collaboration with some others of the Scutoid. So a little housekeeping before we turn it over to Javier to tell us about this fascinating discovery. If you would like to ask a question during the webinar, and I hope you will, because the success of these really depends on your questions, because we do want to talk about what you want to hear about. There is a chat box. If you use your mouse and go over the screen, at the very bottom of your screen, there is an icon that says chat. And then it has a little icon that looks like a cartoon bubble. So click on that and a window will come up, and then you can type your message in the chat box, and I will read your questions and comments to Professor Buceta as we go along. All right, let's get on with it, Professor.
Yeah, so hello everybody. So I have been asked, actually, because probably you have heard about the story about the shape, but I have been asked to give you kind of a motivation how we came with this discovery. So some of the research that we are doing is related trying to understand how tissues are actually formed and shaped. And if you look into any textbook about what is the shape of the cells in epithelial tissues that are actually the kind of the building blocks of all your body from the inside to the outside, you will see something like this shape, like a prism, okay? So we were actually trying to see if what happens with those shapes when there is some level of curvature in some tissues. And that was a relevant question because, as you can imagine, all tissues in your organs and things like that, they have to be subject to some level of curvature in order to accommodate and to develop different shapes. So with that, we actually developed some models. I'm not going to enter into those details, but a prediction of those models was something that was not compatible with this kind of shape. So we have to figure out first what was the shape that we were getting, because at the beginning it was not really obvious. And one of the things that we saw that was particularly strange was that when you were moving from one surface of the tissue to the other surface of the tissue, the cells could actually interchange neighbors, and that will become more clear in a second. So if you think about it and you have two shapes that are actually like this, how these shapes, if they are neighbors, if you go to another surface of the tissue, they can actually have different neighbors. So we couldn't understand that. So at the end, we actually came with a full description of the shape, and that was actually how we discovered the scutoid. So a single scutoid will look mostly like this. And I'm going to show you now this property about exchanging neighbors, because that is something that makes these guys really fascinating. So more probably the image that people have seen the most in the New Yorker maybe is this shape, where they have these weird twists of the shapes. So actually they are like just these two shapes that are kind of similar, but they're actually kind of packed together like this, okay? Now, the nice thing is that when you are actually playing with these shapes, and I'm going to have all the different components that I need here, you can actually pack this without leaving any space. And that is actually something very important because in epithelial tissues, you don't want to leave any space when you are creating an organ. And then you have a perfect packing when you don't have any spaces left in the middle of the cells. But with these shapes, what you can actually achieve is that in this surface of the tissue, you can actually have that the red and the green are neighbors. But when you look into the other surface, the green and the red are not neighbors anymore. And the opposite happens with the blue and the yellow, as you can see here or there. Okay? And that can only achieve when actually you have some level of curvature that maybe you can actually see that in the screen. So that is how we became with the discovery of the shape and this property of exchanging neighbors. Then with the discovery, we went back to the lab, just trying to see, well, is this prediction that we actually got for real? So we actually test in some different tissues that have some level of curvature, and we actually saw that, yes, that was actually true. Cells were actually developing this shape, and the cells were actually exchanging neighbors. What else? Why nature decided to do this weird shape and not a regular prism as the one that I told that is the kind of more common shape that you could expect. We developed some theories and some models based on how much energy these cells need in order to pack together. And what we saw is that when you have some curvature, using this shape is actually something very good for the cells because they have to spend less energy when they're actually packing together. So that's why nature decided to go with this shape and not the regular prism that you could expect. As for the implication of this work, well, there are a number of them. One is for tissue engineering, actually. There are a lot of work now trying to develop good tissue scaffolds that allows cells in order to grow and to develop artificial organs. So with the discovery, what we believe is that this will be a breakthrough because now if you want to develop one of those scaffolds, maybe what you are going to be able is to do that scaffold following the shapes of the cells that actually are more natural when you have some level of curvature. There are also implications in terms of the biology, because when you are actually having this neighbor interchange, the number of communication or the number of cells that is actually communicating with a given cell expands because of this neighbor interchange. And that can be also important in order to improve the cell-cell communication, so we are also looking into that. And something that right now we are very excited is trying to see how was actually the evolution in terms of nature when nature came with this particular solution in terms of evolution. When was the first time that an organism developed this particular shape, because that allowed actually to multiply the kind of shapes that you can have when developing an organ. So we are actually also working into that. I think that this is kind of a brief introduction about how we came with the discovery and why it is important.
Great, thank you. So again, to ask questions, click on your screen and go to the very bottom. There's a chat bubble, and then just type your message where it says type message here. And while you're thinking about those, I have some questions. So the moment that you and your collaborators first discovered, like that you first realized this is something big, this is going to get us in the New Yorker and on the news, what did you do? Did you scream? Did you not believe it? Did you like?
It's a feeling difficult to describe because it's more than knowing that you have discovered something that is going to have a lot of repercussion in the media, or you believe that it's going to have a lot of repercussion in the media, is that moment when you do a discovery and you have found a secret from nature. Wow. So it's like, I have discovered something that nature was actually hiding from us, if you want. That was the most intense feeling that you can imagine. Then, of course, it came like, well, this is going to be huge, and maybe and we were very happy about it, but actually it was that first moment when you are alone in your office and doing calculations and doing things with the computer when you realize, oh my God, I have discovered something that nobody knew before, if you want. So that's something, the more intense feeling.
Right, that every scientist lives for, right? Wow.
Yeah.
We do have a question from Tom Hofaker. How do you determine the amount of energy that cells use for a given shape, and how's the Scutoid saving energy?
Mm-hmm. That's a very good question. So let me try to explain it again with these guys. So when you want to characterize kind of the packing energy that you have, you can imagine that all these junctions between the different cells, if they want to pack and glue together, all the cells, they have to invest some energy. That energy will be coming like, how much energy do I need in order to, if you want, develop the glue that I need in order to pack together. So the way that we did the calculations was actually estimating how much glue do you need, if you want, for creating these particular connections here. And we actually all along the shapes from the top to the bottom. And then what we saw is that that amount of glue is actually minimal when you actually having this shape with respect to the one that you will be expecting if you just have regular presence.
Ronald Bauman has a question. Has this shape been seen in non-biological structures?
No, as far as we know. That was kind of a big surprise, because when we found that, well, this is the shape of the cells, so let's talk to the mathematicians to find what is the name of this shape. The surprise was like, there is no name for that. So no name was actually provided before to this particular shape. And as far as we know, there has not been I mean, describing any other things regardless of the one that appears in cells. Yep.
All right. Another question. You showed us how the 4 prisms interlock in one plane. How do they build in the top to bottom planes, and what is their interaction?
Wow. I am not sure if I understand the question. Can I see the question?
Yeah.
Can I read it again?
Yeah. And are each of them called prisms, or each of them is a scutoid?
In one plane. How do they build in the top to bottom planes?
So maybe like they stack on each other.
Yeah. I'm not sure if the question is how do they interlock in one plane? Well, actually, they do not interlock in one plane, because actually they interlock along this direction from top to bottom. I don't know if it is more clear now that I have only 3 shapes here. I don't know. I'm not sure if that is a question. If it is not, please kind of rephrase it. If you are talking about how they stack in different layers, if you want, we haven't seen any changes in that direction. Okay, but again, I'm not sure if I am totally responding the question.
She says yes, stack.
Yeah. So as for a stack, there is no any particular thing that they are doing. They are just stacking in different planes, following this, but then one on top of another without doing anything weird.
Okay. So each of those is called a scutoid, or those are a prism and 4 of them together?
No. So an scutoid it will be one of these pieces.
Okay. While other people are thinking of some more questions, I had a question about the, one of the uses of this is for tissue replacement and organ replacement, which throws you into a whole nother category of ethics and all of that. Mm-hmm. Have you guys been working with anybody across Lehigh? We're known as a school for a lot of cross collaboration with different departments. Have you been working with anybody at Lehigh or other places to think about that, or is that sort of out of your hands at this point?
Not, we haven't done any collaboration related with the bioethical implications of, if you want about it, if you want something about it. But I have been trying some collaborations. So actually, I tried to convince some people in administration to develop a sculpture about this for Lehigh. And then I was told that maybe some people in some departments in the College of Art and Sciences would be interested in actually develop some projects about how these transcend science and can actually apply it also to art, if you want. And something that we are actually already working is in terms of civil engineering, if you want. So how can we use these shapes in order to build better structures in the macroscopic world?
Right. Yeah, I saw something on social media that someone was proposing, maybe it was you proposing, that the new College of Health should be in the shape of a scutoid.
Actually, I did send a tweet to the new College of Health, like, well, if you are looking for a symbol for the college, maybe you can use this.
That would be fantastic. All right, a question from Joe. Is a single scutoid representative of the shape of a single cell? I think it's if a single scutoid representative of a shape of a single cell assumes in relation to the others around it, and if so, is this present in all tissues you've examined so far?
Let me read it again. If
is a single scutoid representative of the shape of a single cell assumes in relation to the others around it?
That's kind of, it's a difficult question to answer. This is an ideal representation of an scutoid. Basically, mathematically, this is basically described because in one surface, in this case, you have 6 sizes, and in this surface, you have 5. So this shape is going to allow you to lose one of those edges from top to bottom. Okay.
Yeah.
Now, this is, as I said, an ideal representation of what is an scutoid, but the scutoid in general, like a prism, comes in many different flavors. So you can have here 7 and 6, but what you can also have here is 7 and 5, because you actually have this triangle not only in one edge, but in other edges. So this is kind of the simplest case that you have of an scutoid. So this relation between different cells can actually be, in reality, way more complicated than this simple idealized case. So that's kind of addressing the first part of the question. So the second part is, in all the tissues that we have examined, and we have examined different tissues and different organisms, where there is some level of curvature, because again, this geometry is going to appear also when the tissues have some level of curvature, we have found scutoids. That means not only in geometries that have, like, for instance, a tubular structure that are many in your body, like glands, but also in a structure that have more or less spheroidal shape or these kind of things. In all of them, we have found scutoids. But what we are seeing right now is that some organisms, they do not have scutoids, even if they have some level of curvature. That is related with other properties that I didn't mention here, that is like the height of the cells. So if the height of the cells is actually pretty reduced, it's like they don't have time enough in order, or they are not enough tall in order to develop all around this shape. So there are some organisms where the shape of the cells is actually this, they are not very tall, and we have not seen scutoid. But in general, in all tissues and in all organisms, when you have a particular or a threshold level of cells in terms of how high, the height that they have, we have seen scutoids. Yeah.
So the question, how'd you come up with the name?
So we were actually talking about that before this. So there are two versions, or two, the official version and the non-official version for that. The official version is that that is the one that we wrote in the publication, is that if you look in the thorax of some beetles, the shape of the thorax at some point looks like this, okay? I will be able to provide, and if you look in the publications, you will be able to see that. So that part of the thorax of the beetle is called the scutum. That comes from Latin, that means shield. So that's why we decided to go with, from scutum, scutoid. Oid means in Latin similar to. So scutoid will mean similar to the scutellum or to the scutum. Okay, so that is the official version. Now, the unofficial version is that this work was the collaboration between two groups. The group of that I have here at Lehigh, and the group of friend and collaborator that is in Spain, in Seville. And the last name of that other researcher is Escudero. That is actually kind of having the same root of scutoid or scutum. So there was not a fight about giving the name, and we decided to go with Scutoid also because my last name wouldn't be, it cannot have a similarity with anything that you can actually find in nature, like the scutum in beetles. Yep.
Nice. Well, you'll just have to discover something else that you can put your name on. So that's also interesting, is the collaboration between you and I guess it was Professor Luis Escudero.
Yes.
How did that come to be? How did you start collaborating with him?
So I'm going to go back a number of years. So when I was a researcher in Barcelona, I was part of an international course on systems biology. So I was one of the lecturers in that international course, and actually Luisma was up to that point a developmental biologist, but he wanted to become also a kind of a computational biologist, and he actually joined the course. So the first interaction that I have with Luisma was like I was the professor, he was the student. But then with the time I was visiting also for a research stay, I was in Cambridge in the UK, and he was actually working there. And we actually start talking more and more about the kind of things that we work together, because we were both interested in epithelial tissues and developmental biology. And then I was invited to give a seminar in Seville a couple of years ago. And we start talking more and more about how can we collaborate on the kind of things that we were doing. And that is how we started working more and more in trying to understand this 3D structure of tissues. So it was like a first building the personal relation and then trying to work a problem that was interesting from both of us. Yeah.
Very nice. And will you work with him again?
Yes, we are continue working on this problem, and we have conversations almost every week about it.
So now that you've discovered the shape and sort of what can be done with it, what's next?
Yeah, so there are many things that we want to do. So one of the things, as I said, is we are trying to understand better how nature, we know why nature came with this solution. Because as I explained before, it's energetically efficient for cells when you have some curvature to pack like this. But then we want to know now when nature came with this solution. So when was the point in evolution when nature decided, aha, I have found that this is actually a better solution? Because that changed actually what you can do with tissues. And we can actually, we want to understand better evolution and the different shapes that you actually find in nature based on the differences of having this or not having that particular cell shape. So that is one of the things that we are working right now. We are also working in trying to characterize better the energetics of this problem. How efficient or how much energy do you need to pack tissues when you are following that? The other thing that I just mentioned is also related with trying to move forward this discovery in order to understand the implications in the macroscopic world. Can you actually use these shapes like bricks when building a building or not? So the other things are more biological, the cell-cell communication. Other things are related with the molecules, the molecules that actually are able to develop this shape at the microscopic level. We want to understand better all these kind of things. So there are a number of topics that.
Yeah, how do you focus on which things, or you just?
The focus is not the problem. The problem is money and time. So of course, the more money you have, the more students you can hire that can actually work in different aspects of this problem. So with the years, you learn how to be multitask. I would love the day to have 48 hours, but still, I mean, that is not the problem of focusing. So I can diversify pretty easily and work in multitask. The problem is finding more the money and the people, the students that can work in this kind of different problems.
How many students do you have now?
Right now, I have 2 PhD students. I was working with a postdoc that went back to her home country at the beginning of this year, and I'm working with some undergrads. Yeah.
We have a couple more questions that we can get to in the next 2 minutes that we have. Joe asks, can this shape be engineered in tissues that you've worked with so far, or is it only naturally occurring?
Again, it is naturally occurring. And what we believe, what we believe, because it's naturally occurring, is that if you are building like an artificial organ or something like that, the way that normally you do that in the lab is that you kind of create a scaffold that just means that you create kind of a wireframe, and then you seed the cells in order to grow in that particular scaffold, if you want. So what we believe is that if you develop scaffolds and these kind of wireframes following this kind of architecture, the cells will be more happy because they are going to spend less energy when they have to pack together, because they are mimicking better the situation that you will find in a natural organ. So that is work that haven't been done yet, but we believe that is actually a very interesting avenue of research.
Great. And then Trevor asks, and then PW has a similar question about the sheets. How do you determine which scutoids can be combined to form a sheet?
How do you determine which scutoids can be?
And then how do the sheets come together?
That's a kind of a technical thing. I don't know if I have time to explain that. That is kind of based on the computational models also that we have used in order to understand this problem. How these cells pack together, it has been shown already that cells organize themselves following what is called a Voronoi tessellation. That sounds a very fancy and technical term, but it's a way to partition a space, if you want. So that is how you actually determine how these cells are actually kind of creating the initial wireframe and how they are going to pack together. And then, again, that is pretty technical. I will need some blackboards and some things in order to explain you that. But basically what we are doing is following this way of partitioning a space that is called the Voronoi tessellation, and that determines fully what the scutoids you are going to get and how they are going to pack together.
Okay. Great. Well, thank you very much. Our time together is up. So thank you so much for coming over and talking to our alums. And thank you to everybody who was on the webinar. We will be sending you a quick survey to see if you have any suggestions for us. Ronald, I think your question we'll have to ask Javier afterwards. You can type it into the survey and we can send that to him so he can answer you. But great questions, and thank you again. And go Lehigh.
Can I say bye?
You can say bye.
So bye everybody, and yes, that question, they are following geodesic curves.
Oh, good. Good. Done. Thanks.
Thank you.
Bye-bye.